Hello all. In my previous lecture, I discussed temperature effect on diode current, diode resistance, and diode capacitance. In diode capacitance, I think I discussed transition capacitance. Now I think here I will start with the problem. Right? Yeah. Write down. Hello all. In my previous lecture, I discussed temperature effect on diode current, diode resistance, and also diode capacitance. In diode capacitance, actually, I think I discussed transition capacitance and its equation, right? Yeah. Now write down a note actually. Write down a note. See, what is the expression of transition capacitance? The expression of transition capacitance is nothing but CT equal to epsilon into A by W, right? See here, we have two types of junctions actually, abrupt junction, right? See, in case of abrupt PN junction, what is the relation between capacitance and voltage? Actually, CT is inversely proportional to square root of VB. Inversely proportional to square root of VB. And similarly for linear PN junction, the CT is cube root of VB. Cube root of VB. Yeah. See how you got these equations here. See here, CT is inversely proportional to W, right? But W is proportional to square root of VB. In case of linear, actually it is cube root of VB. Now then, what is relation between the capacitance and voltage? CT is inversely proportional to square root of VB. Here it is square root of as the cube root of VB, right? See, from these two statements, what we can understand, for any PN junction, as applied voltage increases, means what is the capacitance here? Decreases. That means here diode acts as a voltage dependent capacitor or varactor diode or varicap diode. Voltage dependent capacitor, varactor diode or varicap diode. Okay. See here, what is the symbol of the varactor diode? See, diode is nothing but it's a two-terminal device. One is anode, another one is cathode, which allows the current in one direction and opposes the current in another direction, right? Yeah, here varactor diode means variable capacitance, right? Variable capacitance includes the variable capacitance. Yeah, this is the symbol of varactor diode. So where we use this varactor diode in our applications? It is used in tuning circuits and also it is used in FM generation circuit. In FM generation circuit, this varactor diode is used, right? Yeah, write out this. Write down, note. Copy this one, two equations here, two conditions, abrupt PN junction and linear PN junction. Yeah, write down. For any PN junction, applied voltage increases, then capacitance is decreases. Hence, PN junction acts as a voltage dependent capacitor or varactor diode or varicap diode. Yeah, underline varactor diode, varicap diode. Okay. Yeah, draw the symbol of varactor diode. Next, copied, right? Yeah, next, applications. It is used in tuning circuits. Next application, it is used in FM generation circuit. Yeah. Write down a question. An abrupt PN junction has Built-in potential of 0.7 volts. Built-in potential of 0.7 volts. Built-in potential of 0.7 volts and junction capacitance. Junction capacitance of 4 picofarad. 4 picofarad at a reverse bias of 1.3 volts. 1.3 volts. If the reverse voltage is increases to 7.3 volts, if the reverse voltage increases to 7.3 volts, then junction capacitance will be right. Yeah, read the question. What is given data? Actually, they given a built-in potential. How much? 0.7 volts. Also, they given a junction capacitance. Junction capacitance is nothing but transition capacitance. How much it is? 4 picofarad. At what voltage? 1.3 volts. If this reverse voltage is increases to 7.3 volts, what is the junction capacitance? This is the given data. See, what is given PN junction? Abrupt. In case of abrupt PN junction, what is the relation between capacitance and voltage? Abrupt PN junction, the relation is CT is inversely proportional to square root of VB, right? CT1 by CT2 equal to under root of VB2 by VB1. What is VB2 here? VB2 is nothing but V0 plus V2. VB1 is nothing but V0 plus V1. What is CT1 here? 4 picofarad by CT2 equal to V0 is 0.7, V2 is 7.3, 0.7 plus 1.3. Then what is C2 here? 2 picofarad. Right? This is the junction capacitance value at the 7.3. Copy. Transition capacitance is completed. And next capacitance, diffusion capacitance. Next heading, diffusion capacitance. It is denoted with CD. Yeah. Copy here. See here, when the diode exhibit diffusion capacitance, when the diode is operated in forward bias, it exhibits diffusion capacitance. See, already we discussed if diode is in reverse bias, how it can access the capacitor, right? Yeah, in forward bias, how it can access the capacitor. You know, one more interesting point here. In case of forward bias, there is no depletion here, region here. Almost depletion is zero, but still the diode, the PN junction acts as a capacitor, right? Yeah, how it can access the capacitor. See, if you want to know this point, actually, if you want to know this PN junction acts as a capacitor in forward bias, please recall the basic definition of the capacitor. What is capacitor? Capacitor is nothing but rate of change of charge with respect to applied voltage. Means if you are varying some voltage, charge also varying, so that structure will act as a capacitor. Here also, in forward bias, what is happening here? See, when the forward voltage is increased, what happens? When the forward voltage is increases, the majority charge carriers are injected from P to N as well as N to P. Okay, you know this injected charge is varied with respect to what? Applied voltage. See, if you are applying more of forward voltage, now then more charge carriers are injected, right? That means here this injected charge is varied with respect to applied voltage. Injected charge is varied with respect to applied voltage means the rate of change of injected charge with respect to applied voltage will call as diffusion capacitance, right? Here the good observation here. See, in case of reverse bias, what is our observation? Immobile charge is varying, but in case of reverse forward bias, here mobile charge carriers are varying. In both biasing conditions, what is common thing? Charge is varying with respect to voltage. See, there immobile charge, here immobile charge, varying with respect to voltage, right? See, what we can understand, in any structure, if charge is varying with respect to voltage, now simply that structure will act as a capacitor. Right. See, the CD equal to what? Actually the rate of change of immobile mobile charge, not immobile, mobile charge with respect to applied voltage will act as a diffusion capacitance, right? So which is equal to tau P by RAC. This is the expression of diffusion capacitance. What is tau PR? Tau P is nothing but carrier lifetime. Carrier lifetime of hole. Okay, what is RAC? Dynamic resistance or small signal resistance. Dynamic resistance is nothing but eta into Vt by I, right? Then what is CD here? CD equal to tau P by eta into Vt by I. So which is equal to CD is equal to tau P into I by eta into Vt. So what we can understand, therefore, in case of forward bias, okay, the diffusion capacitance is directly proportional to current through the diode. Means if current is increases, diffusion capacitance also increases, and it is exponentially proportional to applied voltage across the diode. Exponentially proportional to voltage across the diode. This is the relation between current and capacitance, and also applied voltage across the diode and diffusion capacitance. Okay, yeah, copy here. When the diode is operated in forward bias, when the diode is operated in forward bias, it can act as a diffusion capacitance. It can act as a diffusion capacitance. It can act as a diffusion capacitance, right? When the forward voltage is increases, then the majority charge carriers are injected from P to N or N to P. The majority charge carriers are injected from P to N or N to P. Then the injected charge is varied. Next point. The injected charge is varied with respect to applied voltage. Hence, the rate of change of mobile charge, the rate of change of mobile charge or injected charge, with respect to forward voltage, is called as diffusion capacitance. Yeah, underline diffusion capacitance. That is CD equal to dq by dV. Which is equal to tau P by RAC. Where RAC is equal to eta into Vt by I. Also copy. Yeah, completed. Yeah, next one. Write in a question. A PN junction has a carrier lifetime of 100 picosecond. 100 picosecond, and it is biased at 1 milliampere, and it is biased at 1 milliampere at room temperature. At a room temperature, find small signal resistance. Find small signal resistance and diffusion capacitance. Diffusion capacitance. Diffusion capacitance. Right. See here. What is given data here? They given carrier lifetime 100 picosecond. Also, it is biased at 1 milliampere. What we want to calculate here? Small signal resistance. Small signal resistance is nothing but RAC is equal to eta into VT by I. Actually, in question, silicon or germanium is not mentioned. See, in any problem, silicon or germanium is not mentioned. Consider eta as 1. Okay, eta is 1 and VT is considered as 25. Okay, and I equal to 1 milliampere. Then what is the resistance here? 25 ohms. Okay, this is the small signal resistance. Small signal resistance is nothing but dynamic resistance, right? And coming to the diffusion capacitance is nothing but tau P by RAC. What is tau P here? 100 picosecond by 25. How much it is? 4 picofarad. Yeah, copy. Yeah, completed. So with this example, diode capacitance is complete. With this example, diode capacitance is completed. And the next topic, diode applications. Diode applications. Yeah, so no. See here, we have two types of applications actually. One is analog applications and another one is digital applications. One is analog applications, another one is digital applications. What are the analog applications of a diode? Actually switch. See here, diode access switch, simple switch. See, when it is operated in forward bias, it can access on switch. When it is operated in reverse bias, it can access off switch. But practically, diode cannot prefer the switch because current is uncontrollable. Means in case of diode, third term is not there, right? So it is not possible to control the current. That's why, okay, we can go for three terminal device. So what are the three terminals? Transistor and SCR, right? For low voltage applications, transistor is preferred as a switch. For high voltage applications, SCR can be preferred as a switch. Okay, but diode cannot prefer a switch, even if it can act as a switch because it is a poor switch. Coming to another application, actually clipper. See, my diode also can perform the clipping action. See, clipping action is nothing but removing unwanted portion or undesired portion. Okay, with help of diode, actually we can remove unwanted portion or undesired portion. And next one, my diode also can perform clamping action. What is a clamper? Clamper is nothing but removing of unwanted component. Clamper is nothing but adding of DC component to the input signal. Adding of DC component to the input signal. Okay, because of DC component, actually the signal is shifting either upward or downward. So that can be performed with diode actually. So we can use it in a clamper, right? Next one, it can be used in voltage multiplier. See here, what is voltage multiplier? Multiplier is nothing but which produce a constant DC. That means the output of the multiplier is DC, which is an integral multiple of peak input signal. Integral multiple of peak input signal is nothing but 2 Vm, 3 Vm, 4 Vm, like that. For example, if circuit produce 2 Vm, then we can say it is a doubler circuit. For example, if circuit produce 3 Vm, then we can say it's a tripler. If circuit produce 4 Vm, then we can say quadrupler. Okay, and the next one, here, next one, My diode also can perform the rectification. Rectification is nothing but to convert AC to pulsating DC, right? My diode also can perform rectification, so that's why it can be used as a rectifier. Okay, these are the analog applications of diode. Coming to digital applications, so here we can use the diode in designing of AND gate and OR gate. That means with the help of diode, we can design an AND gate and OR gate. See, NOT gate is not possible with a diode. Why? Because inversion is not possible. With NOT gate is not possible means NAND and NOR is not possible. XOR and XNOR also not possible. Right? See, means a complement cannot be generated with diode actually. That's why we can design only AND and OR gate. These are the applications of a diode. This part actually in detail actually discussed in generally discussed in analog electronics. So here this up to this our diode topic is completed. Means P and diode is completed. Total. Right. Copy. Yeah, completed, right? And next topic, breakdown. The next topic is breakdown. Breakdown. Yeah. So what is breakdown actually? So before going to this breakdown actually, first here we will see the reverse bias condition of diode actually. Reverse bias condition of a diode. See, when the diode is operated in reverse bias, what is the current here? The current is almost constant and negligible. The current is almost constant and negligible, right? Almost constant, negligible. Okay. See, ideally it is zero. Ideally it is zero, but practically it is very, very small value. That is an order of microampere or nanoampere. Okay. This is in case of reverse bias. See, for example, if you make this reverse voltage as very high, for example, if you make this reverse voltage as very high value, then what happened? You know what happened? The current suddenly increased. The sudden increasing of current due to the high reverse voltage is called as breakdown. Okay. You know, a normal diode cannot undergo breakdown here because the maximum power is dissipated at the junction, which may cause the overheating of the diode, due to which the diode gets damaged. This is the drawback of PN diode. See, there is no problem in forward bias. The problem is in only reverse bias. In reverse bias, for example, okay, unfortunately, if you make this reverse voltage as very high, so the diode may chance to damage, right? So here, that is called as, that effect is called as what actually? Breakdown. Okay, right on. Right on the breakdown actually. When the diode is operated in reverse bias, when the diode is operated in reverse bias, the current through the diode is constant and negligible. Constant and negligible. When the reverse voltage is made to very high, when the reverse voltage is made to very high, then the current through the diode suddenly increases. The current through the diode suddenly increases. The sudden increasing of current due to high reverse voltage is called as breakdown. Breakdown. Right? Yeah. Next point. A normal diode cannot undergo breakdown. Because the maximum power is dissipated at the junction. Which may cause the overheating of the diode. Due to which the diode gets damaged. Yeah. Next. Yeah, in case of PN junction, next point, in case of PN junction, the breakdown can be done in two ways. The breakdown is happening in two ways. One is avalanche breakdown, Another one is Zener breakdown. Right now, breakdown can be done in two ways. The first one is avalanche breakdown, and second one is Zener breakdown. Yeah. Next heading, avalanche breakdown. Avalanche breakdown. Yeah. Copy na? Yeah, so no. This avalanche breakdown can occur in lightly doped PN junction. It is occur in lightly doped PN junction at high reverse voltage, due to avalanche mechanism. Due to what mechanism? Avalanche mechanism. Yeah, here for a lightly doped PN junction, see here in case of lightly doped PN junction, okay, electric field is minimum here. See, with minimum electric field, breakdown is not possible. Then what we have to do actually, okay, to make this minimum, we have to make this minimum electric field to maximum. How to make this minimum to max actually? By applying high reverse voltage. That's why avalanche is at high reverse voltage. For a lightly doped PN junction here, electric field is minimum, right? Then to happen breakdown actually, you have to make this minimum to maximum. See, with this, how to make this minimum to maximum actually? By applying some voltage, by applying high voltage. Okay, what I'm saying, it is occurring lightly doped PN junction, right, due to avalanche mechanism at very high reverse voltage. Okay, see here at very high reverse voltage. See, for a lightly doped PN junction, electric field is minimum. Okay, when you apply high reverse voltage, this minimum electric field become what? Maximum electric field. This minimum electric field become maximum electric field. See, when you apply high reverse voltage, now here the electric field will be max. Okay, when the minority carriers enter into this maximum electric field, what happens? Because it is in reverse bias. Okay, so which charge carriers are moving? Minority charge carriers, right? When a minority charge carriers enter into this maximum electric field, it gets accelerated. And it can collide an atom and produce electron hole pair. Again, this newly generated electron hole pair gets accelerated and collide an atom and produce okay, two electron hole pairs. So here this process will continue. Okay, so because of this producing of electron hole pairs, current suddenly increased. Here the current is increases due to what actually? Collision of atoms. Okay, that's why this is called as a collision of atoms. This is called as what actually? Avalanche mechanism. That is nothing but an avalanche mechanism. Collision of atoms is called as what? Avalanche mechanism. Okay. Yeah, copy. Avalanche breakdown. It is occurring lightly doped PN junction at high reverse voltage due to avalanche mechanism. Right? Yeah, for a lightly doped PN junction, electric field is minimum. Yeah, next point. When high voltage is applied, minimum electric field become maximum. Yeah, underline minimum electric field become maximum, right? Next point, when a minority charge carrier is enter into a maximum electric field, when a minority carrier enter into a maximum electric field, and it gets accelerated, and collide an atom, and produce electron hole pair, Next point, this newly generated electron hole pair, gets accelerated, and collide an atom, and produce extra electron hole pairs, due to which current suddenly increases. Next point, this sudden increasing of current due to collision of atoms, is called as avalanche breakdown or avalanche mechanism. Underline, current suddenly increases due to collisions of atoms, is called as avalanche breakdown or avalanche mechanism. Yeah. Completed? Yeah. Next one, Zener breakdown. Next topic, Zener breakdown. Breakdown. Yeah. So what is Zener breakdown here? See, Zener breakdown is occur in a heavily doped PN junction. See here, this is lightly doped PN junction. It is occur in heavily doped PN junction at small and medium reverse voltage. Due to what? Due to Zener mechanism. Yeah, why it is small and medium reverse voltage actually? Because of heavily doping. In case of heavily doping, electric field is maximum here. In case of heavily doping, electric field is maximum. Okay. If you apply high reverse voltage, now already electric field is maximum. If you apply the high reverse voltage, this maximum electric field become very strong electric field. What happened? The diode may chance to damage. That's why apply small and medium reverse voltage. See, if you apply small and medium reverse voltage, actually what happened? This maximum electric field become further be strong, which is sufficient for breakdown. Further be strong. Okay. What happened? Further be strong, due to which covalent bonds can break. Okay. Covalent bonds can break and produce electron hole pairs. Okay. Due to which current suddenly increased. Here the current suddenly increases because of what actually? Strong electric field. Here a collision of atoms, here strong electric field. This breakdown is called as what? Zener breakdown. Write down this. It is occur in heavily doped PN junction. At small and medium reverse voltage. Due to small and medium reverse voltage due to Zener mechanism. Yeah. Next point, for heavily doped PN junction, electric field is maximum. Yeah. Next point. When small and medium voltage is given, applied, maximum electric field become strong electric field. maximum electric field become strong electric field, due to which covalent bonds can break, due to which covalent bonds can break, covalent bonds can break and produce electron hole pairs, electron hole pairs. Due to electron hole pairs, current suddenly increases. Due to electron hole pairs, current suddenly increases. This sudden increasing of current, this sudden increasing of current, sudden increasing of current, sudden increasing of current due to strong electric field is called as Zener breakdown. Is called as Zener breakdown. Yeah, underline sudden increasing of current due to strong electric field is called as Zener breakdown. Yeah, this is about two types of breakdown. Yeah, copy if you want diagram. Copied, right? Yeah. Next, next, Zener diode. Next topic, Zener diode. Zener diode. Yeah. So now what is Zener diode actually? Zener diode is called as a special diode. Zener diode is called as what actually? Special diode or breakdown diode Why it is called as breakdown diode or special? Because it is specially designed for breakdown. See, what is the problem in normal diode? It does not operate in breakdown, right? That's why we want a special device to operate in breakdown. The special device is nothing but a Zener diode. See, what is the basic difference between a Zener diode and a PN diode actually? Doping concentration. Okay, both are a PM, both are PN junctions, but the basic difference is the doping concentration. Because of heavily doping, okay, in case of Zener diode, it can be operated in breakdown. It can operate it in breakdown. Okay. Next, what is the doping concentration in case of normal diode and Zener diode actually? In case of normal diode, the doping concentration is like this. That is 1:10 power 8. What is the meaning? For 10 power 8 silicon atoms, 1 impurity is added. In case of Zener diode actually, in case of Zener diode, what is the doping concentration here? 1:10 power 5. That means for 10 power 5 silicon atoms, how many impurities are added? 1. That means which one is heavily doping? Zener is heavily doping compared to PN diode. Because of this heavy doping, it can operate in breakdown region. Okay. And one more point actually, so Zener diode is a heavily doped PN junction. That means what we can understand, Zener diode is a heavily doped PN junction, due to which the electrons are tunneling from P to N or N to P. Why electrons are tunneling? See, in case of normal diode, electrons will crosses over the barrier, but in case of Zener diode and tunnel diode, the electrons are penetrated or tunneling through the barrier. Why it is tunneling or penetrated? Because of thin barrier. When doping is increases, depletion width is decreased. When doping increases, okay, depletion width is decreased, right? So if depletion width is decreases means then why electrons will crosses over the barrier? Why electrons will travel like this? No, it will penetrate the barrier. This is called as tunneling mechanism. We can observe complete tunneling effect in tunnel diode, partially in Zener diode. Right? Yeah, right on. It is a special diode. It is a special diode or breakdown diode. Special diode or breakdown diode. Breakdown diode. Because it is operated in breakdown region. It is called as special diode or breakdown diode because it is operated in breakdown region. Next one. Zener diode is a heavily doped PN junction. Zener diode is a heavily doped PN junction. Due to which electrons are tunneling from P to N or N to P. Electrons are tunneling from P to N or N to P. Right? Yeah. Copy these concentrations here. Doping concentrations. PN diode 1:10 power 8. Zener diode 1:10 power 5. Right. And one more. See, coming to the operation of Zener diode actually. See, coming to the IV characteristics. When the Zener diode is operating forward bias, when the Zener diode is operating forward bias, what about the IV characteristics? The IV characteristics are similar to normal diode characteristics. Like this. Okay? Because in forward bias there is no problem here. Whatever the characteristics normal diode have, the same characteristics Zener diode also. Okay, even if you change the doping concentration also. See, if you change the doping concentration, cut-in voltage never change, right? It should be a 0.7 or 0.3. Okay, then characteristics also same. Now coming to reverse bias. When the Zener diode is operated in reverse bias, the characteristics are similar to normal diode. Right? It is also same. What is the specialty here? Specialty is called as a breakdown. Breakdown is nothing but sudden increasing of current. Sudden increasing of current. Okay. See what we observed. In case of normal diode, it has only two regions: forward bias and reverse bias. But Zener diode has three regions: forward, reverse, and one more actually breakdown. Breakdown region. It is also operated in breakdown region actually. Right. This is about practical characteristics. If you see the ideal characteristics, the characteristics are like this. Characteristics are like this. See here I am changing some modification. Actual characteristics, ideal characteristics are like this. Diode ideal forward characteristics. And here like this. But here I am changing because of to draw the symbol actually. This is an ideal characteristics. See the ideal characteristics. What is the diode? Actually diode is nothing but it's a two-terminal device, right? One is anode, another one is cathode, right? And oppose the current in another direction like this. This is a symbol of a normal diode, right? Here I can also include characteristics in the symbol. You know, this Z shape indicates not Zener. Here it indicates simply characteristics. Characteristics of Zener diode. Actually one is a forward characteristics, another one is breakdown characteristics. Okay. Copy. Yeah, completed. Yeah, now coming to breakdown voltage here. Breakdown voltage. What is the breakdown voltage? This VZ is nothing but a breakdown voltage. What is the breakdown voltage? Breakdown voltage is nothing but the applied voltage at which current suddenly increases. That voltage is called as breakdown voltage. Okay. Here this breakdown voltage will depends on what? This breakdown voltage depends on doping concentration. Breakdown voltage will depends on doping concentration. How it will depends? Inversely proportional. Doping concentration. Very, very, very important relation. See, just now I told in case of forward bias it has only two regions, forward bias and reverse bias. Why it is coming? Because of changing of doping concentration. That means here this breakdown voltage depends on doping. If you decreasing the doping, there is no breakdown. It's like normal diode. If increasing the doping here, there is a breakdown, right? That means here the breakdown voltage will depends on what? Doping concentration. How they related actually inversely proportional. Inversely proportional means when doping is increases, breakdown voltage decreases. When doping is decreased, the breakdown voltage is increases. Okay. And one more important point actually. See, when the Zener diode is operating in breakdown region, the current through the Zener diode is increases or decreases. But what is voltage across the Zener diode? Constant. Voltage across the Zener diode is constant, so that it can access a constant voltage source. It can access a constant voltage source. Yeah, because of this one actually, because of these special characteristics, it can be used in regulators. My Zener diode acts as a regulator. Also, and one more application, it can also use in voltage limiter circuit. Voltage limiters are nothing but clippers. My Zener diode also acts as a clipper. Okay, right on. Right on, please. The applied voltage at which current suddenly increases. Is called as breakdown voltage. Yeah, copy this relation. Breakdown voltage is inversely proportional to doping concentration. Next, write down. When the Zener diode is operated in breakdown region, the current through the Zener diode is increases or decreases. But voltage across the Zener diode is constant. Therefore, it can act as a constant voltage source. Underline constant voltage source. Right? See the equivalent circuit in forward bias and reverse bias actually. See, when the Zener diode is operated in forward bias, what is the equivalent circuit here? Short circuit, because whatever the characteristics normal diode have, the same characteristic. That's why equivalent circuit is same. When the Zener diode is operated in reverse bias, actually what is the equivalent